Hello, I am Pamela Fox, and I'm talking about pgvector for Python developers. pgvector is a great extension that you can use in order to store vectors in your database and then do distance operations on them. It's incredibly useful if you're doing any sort of similarity search, especially for generative AI applications like retrieval augmented generation in order to search and chat with items in your database. So come to my session to learn more about pgvector for Postgres and Python. Welcome, everyone. I'm going to be talking about pgvector for Python developers, bringing together my two favorite things, Python and Postgres, and then my third favorite thing, vector embeddings. So I'm going to start with just an overview of vectors and what I'm even talking about. A vector is a list of numbers. It's a list of floating point numbers typically, and this list of numbers represents an item in a high dimensional space. So here in this graph, I'm showing vectors that have 3 dimensions, but typically we work with vectors with much higher dimensions, and those are just harder to visualize. So for the string apple, we have an example vector here, and then we could also have a string for oranges, and the vector. We're trying to compare these two vectors. This oranges vector has another set of values here. So you can think of this, we call the list of floating point numbers. It has a length. We also call that its dimensions, because we consider each of those numbers to be a dimension in the space. And the tricky thing is, what do each of these numbers actually represent? A lot of times we don't really know what each of those numbers represents. We just know that there's some sort of dimension they represent of that vector. So we use a model in order to generate a vector for a particular piece of content. So for example, we could take the word dog, and then we pass it through this machine learning model. We could use like a word-to-vec model. That is one way of generating embeddings for single words. And then we get back a vector, and that's the list of floating point numbers. We could do the same thing for other words here. So like cat, and we get back a different list of floating point numbers. Now, there are many models that you can use to generate embeddings. And what matters about the models is what kind of input can you give it? And then how big is the vector that comes out? And what are the characteristics of that vector? So for example, these are some of the most popular models. Word2Vec is a model that we've had for many years now, but it only takes a single word. And then the dimensions that come out can be anywhere between like 50 and 300. Now, more recently, we'd have these models come out from OpenAI and from large language models generally that are able to take in large strings of text. And that's made for much more interesting applications. So for example, with OpenAI, it can take in a text of up to 8,192 tokens. And those dimensions vary. One of their models has 1,536 dimensions, and then their newer models actually can vary between 256 and 3,072. So you have high variability in how long the text is you can pass in, and then high variability in the actual dimensions that come out. There are also embedding models that can take more than just text. So we, at Azure, they have the computer vision multimodal embedding API that can take a text or an image, and it has dimensions of 1024. Now, there are quite a few other embedding models. Many of them are open source, so you can find them at Hugging Face, and there's even this leaderboard that tries to compare the different models to see how well it does in different data sets. So lots to explore in terms of what models you can use in order to generate vectors. So once we have the models, why do we even care? Why do we want to go through all this effort to turn our data into vector embeddings? Well, once we have data represented as vectors, now we can suddenly do really interesting things. So we can start off with similarity, right? We can say, okay, these 2 items are more similar in the data set than these 2 other items. And that can be great for recommendations, for, doing like fraud detection. There's lots of things you can do once you can look at similarity. We can also do search, which means getting an arbitrary new input and turning that into a vector, and then using that vector to find things that are similar to it. And we're going to see how to build both similarity and search algorithms here today. Now, I have some tools to help me understand vectors. So here's one where I visualize vectors across a few models. So we have Word2Vec versus OpenAI. And so you can see with Word2Vec, our vector has 300 dimensions. With OpenAI, it has a whole lot more. And what I've also shown here is just within this particular word set of 1,000 words, what are the most similar words to this input, right? Because they're talking about being able to do similarity algorithms. So for dog, the most similar one is cat for Word2Vec, which makes sense. For OpenAI, it's God, which is interesting. And what you can see here is that different models encode different things in their vector space, right? So Word2Vec is, you could say, almost like purely a semantic space where it cares about the semantics of words and how they show up next to other words in different contexts. So dog and cat are so incredibly similar because they're both pets. Cats are better, but they're both pets. OpenAI also tends to encode things about the syntax and the spelling as well, and so that's why we see that God is the most similar to dog in this list. So I find this really interesting just to get an idea for the fact that, within different vector spaces, you're going to have different results when you're doing similarity and when you're doing search. You can also look at, what is the least similar, and you can also kind of see the range of, how the similarity distance is. And this is the way we're, calculating this. So that's one way that I try and understand vectors. Another really fun tool is this from projector.tensorflow.org. And this tries to visualize these vectors in three-dimensional space using a principal component analysis to reduce the, very large vectors into just 3 dimensions. And, it does a pretty good job. Now, it's really, really hard to reduce, these very high dimensional vectors into much lower dimensions and really be able to represent all the complexity of what's encoded in their space. But it's pretty fun to look around and visualize and see what's most similar to IP is TCP and routing. That's great. Analog, magazine, highways, road. So this is just another way to get yourself accustomed to thinking about vector spaces. But remember, it's much more complex than we can ever visualize in 3D. So how do we actually measure the distance between two different vectors, right? We need to be able to measure distance if we're going to do any sort of similarity or search. And there's a number of different distance metrics. And, these are all actually supported by Postgres. So the first is Manhattan distance, also known as taxi cab or L1. And it's known as taxi cab because it's literally like if you have one location and another location in a city, what are the streets that a taxi would have to go down? Or like in this grid here, what are, it has to travel along the grid, how does it have to travel in order to get from the end of V1 to the end of V2? So we can see for this, for these two vectors, 1, 2, 3 and 3, 1, 2 in this 3-dimensional space, the Manhattan distance is 4. There's also Euclidean distance, which is the straight line distance, right? The as the bird flies. And, typically we would use this over Manhattan. This is known as L2 distance as well. Now, a more interesting one is the dot product. It's called the inner product, the dot product. It has a few different names. And this is, it's actually like projecting one vector onto the other and then figuring out the area between them based on the angle. And it ends up producing actually a scalar value, this number. So for these ones, it produces a value 11. And that's the way we can think about, how close these two vectors are. A variant of this is cosine distance, where cosine distance, we care about the angle between these. And these two are actually the same if your vectors are normalized. And as it turns out, many vectors are normalized, as in their unit vectors. So if your vectors are normalized, these are the same, and the dot product is actually the more efficient one. Okay, so though that is our Vectors 101, you can get way deeper into that if you're interested. Lots of great resources out there on the web. Now let's talk about how we store vectors in Postgres. The first step is to use the pgvector extension. And there is a great GitHub repo where you can get the instructions for how to install it. So I've got it installed locally here in a VS Code environment here. And I've actually got it installed inside a dev container, which is basically like a Dockerized development environment. So I set it up using a Docker compose.yaml so that I could bring in pgvector. And so here I have the very latest one because I wanted to get this new operator they just added. And yeah, so that sets up a Postgres server that is running inside my container. And you can see that it's running here on port 5432, which is the default. So I've got that running inside my environment here. And that's gonna, make it so that I can use the extension. But then the first thing you need to do after you have the capability of using the extension is to actually run this create extension command here on whatever database you want to, use it with. So we'll go back to here, and I'm going to use my SQL tools extension in order to run SQL. So I'll just run this. And boom, it worked. No results, but it worked. So that's good. That meant it knew how to make the extension. Now, notably, the extension is called vector, not pgvector, which is actually, I think, the most confusing part of pgvector is that the extension is called vector. All right. So now we've got that extension. Now we should be able to actually use it. So what we can do here is first we can create a table that has a vector column. So this is a new type that's introduced by the vector extension. And we tell it, okay, we want it to be a vector column and we want it to be 3 dimensions long. So we're going to start with just our, our small vectors. So let me run that. First, let me actually drop it because I bet you it already exists. Let's see. Okay, dropped it. And now I'm going to make it. All right. And the next step, we're going to insert some vectors into the table. And so here I'm specifying the vectors using an array inside quotes. That's one way we can pass them in. So I inserted them. Now, do they exist? I can actually just use SQL tools and check out the table and see that, yep, we do have 2 rows and they're storing vectors. Now we can start querying. So we can use the select. Let's do this one. So this one does a select from items, order by the embedding column. Remember this embedding column? It's distance from 312. So we're curious about how, what are the closest vectors to 312? And then it'll get the top 5. So let's run this. And here we can see that it thinks that this one here, 456, is the closest one. We can also ask explicitly what is the distance between them, right? So the way we did, do this one is we're actually going to put that expression in the select. So we have select, embedding, distance from, so this is the distance operator we're using here, distance from this target vector, going to alias it to distance and get it from the items table. So we'll run that. And what we can see is that the distance for the first one is 214 and the other one is 116. Okay, so we've been able to store items, we've been able to query, and we've done this all with just pure SQL statements. And they're all working, which is great. Now, you saw that I was using this operator here. This is one of the distance operators. This is actually that's the cosine distance operator, but we've got 4 different options. So the same distance things I showed before, we can do all of that in Postgres with a pgvector extension. So we could do Manhattan, right? So we could go and change this to Manhattan, and we can see 4 is the answer there, right? We could do the dot product as well. And we can see -11 and -29. So this one's actually the negative dot product, just because of a detail of how pgvector implements this. They take the dot product and then they negate it. We did the cosine distance already. we can do Euclidean, and then something interesting is actually going to happen. Oh, actually, Euclidean worked this time. Okay. Sometimes you may get an error because this operator is also used by Postgres for other things. So sometimes it has a hard time telling when you're trying to use this operator for vectors versus other things, like if you have the PostGIS extension. So if all else fails, you can also use the function. You could do, L2 distance, embedding, and then our other vector, and run this. And we get the same results. So you might be wondering which of these distance operators to use. Generally, the one I would recommend is the dot product, especially if you're working with OpenAI embeddings, which is what many people are working with these days. Then I would recommend the dot product. Lots of people are recommending cosine distance, but in fact, the dot product would be more efficient because it's actually the cosine distance is, you need that if you've got non-unit vectors, but if you're working with normalized vectors, you can use dot product and it's more efficient. So that's what I would tend to recommend. But generally, you can just look up for the model and say, okay, for this model, what distance operator should I be using? And you can also, do some comparisons in terms of time and accuracy and all that. Now, I've only shown you, these really small tables. We could potentially be storing thousands, millions of vectors in our table. How do we do these queries in a fast way? So we generally are going to want to add an index that can do an approximate nearest neighbor search. The most popular index these days, it's HNSW, which stands for Hierarchical Navigable Small World. So we can do this create index command that will tell it like, hey, we want you to create an index using HNSW. And we tell it, here's the column for the index. And here is the operator you're going to use. So in this case, we're using inner product. Because remember, I just said that's what I would recommend, especially for the OpenAI embeddings. So we can run that, and that creates an index. There's a lot more configuration you can do for an HNSW. So if you're curious about HNSW, there's a great tutorial here. There's great videos online with more information about the different parameters for HNSW. Because generally, they're going to affect your precision, your recall, your speed, and you have to figure out what's going to work for you because this is an approximate nearest neighbor search. So as soon as you start using approximations, you do risk accuracy. So you do want to consider that in terms of what index you use. There is one other option you can use with pgvector, which is IVF flat. I haven't actually personally used that myself because I always use HNSW, but it's another option, and there might be some situations where it is the better option. All right, so finally, let's talk about pgvector with Python. So once you understand how to just use pgvector with Postgres, using it with Python is actually, I think, fairly straightforward. You can install this pgvector Python package, and it's built by the same people who create the pgvector extension. So it works really, really well with it. And it comes built in with support for all of the best Python packages. So psycopg, asyncpg, SQLAlchemy, Django, all the ORMs you would think about using. And it has great examples in the repo. So let's go ahead and check out some of those examples here. So in this environment here, I have a bunch of the examples from that repo, right? So here is with psycopg, that's just running all the stuff that we ran in the SQL tools. We could run this, go to the terminal, right? But what's more interesting is using an ORM, because if we're using it from Python, we probably do want to use an ORM. My favorite is the SQLAlchemy ORM, right? So in that ORM, I can declare my rows using Python classes, and I can say, okay, I'm using vector, and that vector class comes from the pgvector Python package. So I say, okay, I'm using vector, and it's got 3. And then, I'm going to create this index, and here's these additional options I was telling you about, like EF construction. Then I add my items, and then, I'm doing some distance operations here. And I get the same results, except I did it with an ORM. Now, a more, interesting example, this one is with movies. And what I did is I took movie titles and I embedded them using the OpenAI embedding models. So this time I have a vector of 1536 dimensions, and I've got a bit more data than I had before. Still not a huge amount, but a little bit more. So I'm going to run this one. And it's going to try and find the most similar movies for Winnie the Pooh. And it's just based on the embedding of the title, not of the description or anything like that, just the title. So here we can see the most similar ones in Winnie the Pooh are other Pooh movies, which makes sense. And then also Pinocchio, which makes sense because it's a toy come to life. And then Alice in Wonderland, once again, toys come to life. So it's really, really interesting when you start to, play with these embedding spaces to see what it thinks is most similar for a particular input, right? And this is just based on the titles. If I did the entire movie description, we would see much different output, right? For Frozen, all the most similar things are actually related to like water and cold, because Frozen, it doesn't think of that as a Disney movie. It just thinks of that as the word frozen in this particular embedding space. So really, really interesting. Okay, so we've got, these are some examples where we can see how we can work with SQLAlchemy. Now let's actually use this for a full app. So going here, I have a FastAPI app. So this is, one of the most popular ways of building APIs in Python. And I can show you the FastAPI app here. This is the auto-generated documentation. So we've got operations for getting an item by ID, for getting the most similar items to something, and then for searching. So let's try if we get an item by ID. This is just doing our, a standard SQL call. And so we see this is a database about camping gear and like recreational gear from a store. So we get back these boots. And now if I want to do most similar, I'm going to say, okay, get me the most similar items to item 1. And I execute that. And I see what I get back is a bunch of boots and shoes. So let me show the code for that. So in this FastAPI app here, we can see this is a similarity handler. And what you can notice is that I am using async. Since this is FastAPI, we want to be able to use async. This is going to enable better concurrency once we go live to production with users. So general tip is to always use async, and you can use SQLAlchemy with async. So that's what I'm doing. I get the item by ID, and then I do the same operation that I've been showing all along, which is, let's get the item, let's get the distance from the item, let's exclude the current item, and then order by the distance. And then I return the item's dictionary plus the distance so that when we look at the results, we can see, okay, here's the matching items, and here's how similar we thought they were. And then finally, we can do search. So with search, I can input an arbitrary new string, right? So I could do boots, right? And if I do boots, then I get back the things that matches boots. And it's doing both a vector search and a text search, combined together. So we get back lots of boots. I could also search in Spanish because it's going to work because of the vector search. So Spanish gets back boots as well. I could even be really colorless footwear, right? These are words that don't appear in my descriptions at all. But if I search colorless footwear, I get great results. I get gray trail shoes. I get clear hiking shoes. And I get black hiking shoes, colorless footwear. So this is the great thing about vector search and vector embedding spaces, is that then a user can type in, other languages. They can type in, strange, obscure descriptions like colorless footwear, and you can still get a match. If I disable vector search here and then I search for colorless footwear, I get no results at all. So this is really, really powerful. So let's take a look at how this is actually implemented. So here's our search handler. So let's go here. So the first thing we do is that we turn the input query into a vector. And then we use that to do a SQL query. So this is doing a combination of a vector query using pgvector. So this is the vector query. This is doing a full text query using Postgres full text search, capabilities, built-in capabilities. And this is using, the text version of the query. So this is using the vector version of the query. This is using the text version of the query. And then we combine them together. and we merge them together. We compute a final score using this algorithm called reciprocal rank fusion. And that gets us the merged results. And then we can return back those merged results. So this is what's known as a hybrid search. And this is the best practice for how you can take a user query and search a database and get back the best results. If you use both vector search and full text search, which we can do in Postgres very well, then we can get these amazing results here. So there we go. That is how we can, build many very useful and powerful APIs using pgvector in Python. All of the code that I've showed you is open source, and you can go and check it out. And you can find even more examples in the pgvector Python repo. So I definitely recommend checking that one out as well. And you can get my slides from this URL here. So if you want to follow any of the links that I showed, just go to the slides and follow the links from there. And I'm, happy to take any follow-up questions online over, all the different networks, and just hear, how people are using Postgres with pgvector and learn more from all of you. I've only learned it in the last year, and it's been great to see all the resources that are there. And I'm trying to put more resources out there in the world based off of what I've learned about using it. So thank you.